Okay, so let's begin. So we're going to look at Kruskalls again. I felt this was covered reasonably okay. This was before got a little sick. So it should be okay. But we're still just going to go over again. So how it basically works is that we want to find a minimal spanning tree. There's a few ways to think of it. I don't know, I think of them very weirdly, and people typically don't get the way I think of them. But the kind of mathematical definition is that you want to make it such that all the weights is minimized. So you want to find the minimized version of this. So sum up all the little weights here, and you want to minimize them, but you need to satisfy a condition. And the condition is there must be only one path to every node. Right? From a given node. So if I start here, there must only be one path to 2. In this case, as you can see, there's 2 paths, or there's many paths. I can go down here, I can go back up. I can go down here, go across, I can go back up like this, right? And so all those little infinite paths means that we're breaking the condition of a minimum spanning tree. So an example of a spanning tree would be something like this. This isn't necessarily minimal, but it is a spanning tree. And the reason why is because there's only one path to every node. So if I want to go from 1 to 3, I've got to go down here, across, and up. That's my only path. Because if I go down here, I can't come back, right? So obviously when I'm talking about path, I'm talking about the ability to only visit every node once, right? Okay. And obviously we can talk about like Hamiltonians and stuff here, right? So for example, a Hamiltonian circuit would just be, well, really anything here, right? There's quite a few Hamiltonian circuits. Like all of this, that's a Hamiltonian circuit. Like we're visiting all the vertices once. If we wanted to do a Eulian circuit, or Eulian tour, there's some is called circuits, some is called tours. It's the same thing. We would just have to visit all the edges. So that's probably not going to be possible. Already I'm looking and going, I don't think we can. Yeah, no, we can't, because we get to this situation here. But there's enough that makes me think it's probably possible. Yeah, it is possible. Okay. You just have to do this. Up, across, down, left, up. And you can start at 2 here, I think, and still be possible. So I think it's possible. Oh, there's these 8 and 4 here. That makes it kind of tricky. I don't know. I think it's possible, but I may be wrong. Who knows? Doesn't really matter. You can sit down and try to figure out if you can. So Kruskalls is just based around just choosing the minimal edges. So we're just going to go, okay, let's be greedy. And let's just presume that if we choose all the smallest ones, we'll eventually reach a spanning tree. And eventually, once we reach that spanning tree, we'll be done, right? Because obviously if we always choose the smallest ones, then we must always have something that's minimal, right? This is kind of like how the greedy part of it works, right? So almost all greedy algorithms work by basically presuming something. So in this case, we're presuming that if you grab the smallest ones, we're going to get a min. So grabbing smallest, we'll get a minimum spanning tree, right? And then you always need a case. Basically, you need to fix up. So there's 2 ways you do it. The first one is you could either have a fix up, or the second one is you could, prove it never prove always right. This is often not very possible for greedy algorithms, so often you always have some kind of fix up. So in this case, our fix up is check if it is a cycle. And if it is a cycle, then delete at the edge. Right? So in this case, let's just replicate the tree and replicate somewhat correctly. There we go. That's okay. And I did it wrong. That should be 6, that should be a 3, and that should be a 1. Okay. So we're just going to begin by grabbing all the smallest edges. I'll just grab these first 2 very simply, because they're the easiest ones. Now I'll also grab 3, 4, that's okay. As I said, just keep grabbing all the edges. And only once you find out there's a cycle, or there's more than one path, i.e. once this condition is invalidated, that's when you go back and you have to remove things. So in this case, we've added that, now we can add 1, 2. And you'll find that 1, 2 is still fine. Right? We still haven't broken anything. But when we go and try to add 2, 4, i.e. when we go and add this, we find that now from 2 we can reach 4 two ways. We can go from 3 and we can go to 2, two ways, right? So we can go, this is a highlighting, I don't know, is that a good one? I guess laser pointer, sure. We can go along here, up, then across. We could just go straight up to it. You know, there's a large majority of routes. So in cases like that, we want to undo it. Of course, I undid the wrong one, but that's okay. We want to undo this one here. Because we obviously, between these two paths, you know, between these two weights, we want to choose the smallest one, right? Because we want the smallest weights. And then we keep going, and we're going to add, I guess, the 10 here. Well, no, sorry, not 10. We're going to go to the next one, we can add 1, 3. Again, if I add this, we're going to get a cycle, you know, the triangle. So ignore that. Go to the next one. 4, 7 is okay. There's no cycle here. There's only one path to every node. I like thinking of it as paths because it's kind of probably the most accurate version of it. The other ones are less accurate. It's up to you. 3, 6 is going to cause a cycle. 5, 7 is not going to cause a cycle. So we're going to choose that as our last one. And the other ones we're still going to process. There are ways that we can get around processing them, and you see them in the algorithm. Sometimes we'll go, well, the number of edges is less than the number of vertices minus 1. And the reason that we can do that is because in this case, if we only have one path to every node, then basically every node can only own one line. I guess you can say it that way, right? With the exception of 1. So in this case, we can say this line here is owned by 2. So therefore 1 will own this line. You know, 3 owns this line. 5 owns this line. 6 owns this line, and 7 owns this line, and then 4 is left with no line. Another way you can think of it, and I kind of prefer this, is that you double both of them almost, and you say that basically you're counting the number of paths between them. So you say, okay, 1 and 2, there's a path between that. There's a path between this, a path between this, a path between this, and a path between this, and a path between this. So it's almost like you're saying 2 times the number of edges is less than 2v minus 2, right? And so you're basically saying, if I'm going to double the number of edges, i.e. double count it on both sides, I want to make sure, I guess I should say equal here, not less than. You want to go while this is true, but you want to stop when this is true, right? And the explanation for this, I mean, you can just see it by arithmetic, but the explanation is that you want to say this path is owned, or this edge is owned by both of them. So you want to say, okay, you know, this vertice and this vertice own this one. But the point is that then you also get cases like this, right, where one has now got 2 paths that it owns, right? So each vertice can only own one path, or can only own one edge. If a vertice owns more than one edge, then it means that you have more than one path. For example, here, right, 3 owns this one, and 1 owns this one. So this one is taken up by 1 and 2. This one's taken up by 3 and 4. This one's taken up by 1 and 4. But we can't do this one here because then, you know, these ones would have an extra path on top. Right? So we're going to end up with a duplication. I don't know. Maybe that doesn't make sense. But let's actually go to the actual question next. Okay, so the next one, of course, it's spawned that, which is not what I wanted. I could go away. So now we're here. Yep. And we're just going to go through the kind of Dijkstras using this system here and see whether or not it's quite nice. Okay, so we're searching from 0, so we're starting here. Now, Dijkstras is effectively, as I said before, it's just BFS, which is, you know, breadth first search, right? Which means that we're going to use a queue. But the only real difference is it makes this a priority queue. I can't spell. This still that's wrong anyway. That seems right to me, but also it doesn't. Anyway, who knows? So we're going to make it a priority queue, which in fancy words basically means that we're always going to choose the smallest cost to visit next, if that makes sense. So it's kind of like Kruskalls, which is why I'm doing it in this order. In Kruskalls, we always chose the smallest edge. In this case, we're doing the same kind of thing, but instead of choosing the smallest edge, we're going to choose the smallest path. So effectively, what we're saying is we're saying, okay, from 0, here we are. What's the smallest path that we can take to a node? And the only small path that we can take here is either this one or this one. They're the only two paths from 0. So we're going to take the smallest of them. We're going to go, okay, go down here. Because what this immediately tells us is this immediately says, if you want to go from 0 to 4, there's your smallest path. We've already got it. That's it. That's the smallest path from 0 to 4. It also tells us the smallest path from 0 to 3, potentially. Right? And this is why I'm saying we want to grab the smallest one. Because what we may find is we may find that there's this really cheap path from 4 to 3. Like this. That's only got a cost of 1. In which case we've got a smaller path. And that's why I'm talking about the fix-up before, right? All these things is guessing. It's guessing that, hey, if we go 0 to 4, this is most likely the smallest path. It may turn out that it isn't, and that's okay, and we'll fix it up later. Now this I'm going to rename as predecessor. And cost, and I don't really care about the known, but that's just basically our vertex set. There we go, it's back. I'm going to just clear up some space. Okay, and the known is just our set to basically say, hey, whether or not this thing's been visited. The one really nice thing about this is that you don't have to use a priority queue. You can just use an array, this is a very quick way of writing it. And you just use an array, and then what you do is every single time you search through that array and you find the smallest. Effectively, that's the exact same thing as a priority queue, right? Because a priority queue is just a queue where it chooses things based on the smallest value. And that's effectively what you're doing there for an array, right? You're just choosing the smallest cost from here. And so even though I talked about priority queue here, we're just going to choose the smallest cost. Because once you actually have two nodes, it doesn't actually matter which one you choose if they've got the same cost. Which is kind of a bit weird. Yeah, so effectively the algorithm is very similar to BFS, just with a queue, with a priority queue. Oh, why am I drawing here? Okay, so we're gonna follow it along, and we're gonna step forward one, and we're gonna find what happens. So we're gonna start at 0. Yeah, okay, we set the cost to 0. We say it's known. Okay, sweet. Next, we're going to set the children. No, this isn't actually visiting the children. It's just setting and saying, okay, I could go to these two children. See how it sets the processes and the counts? Okay, so what we're saying here is we're saying, okay, from 0 to 3 there's a path, and from 0 to 4 there's a path. So let's add them. All right, just what I was saying before. And then it's going to visit the children based on the smallest path. So it isn't going to go to 0 to 3 first, it's going to go 0 to 4. Okay, so we can go back to our pointer, step forward, see how it jumps to 4. Awesome. It's now going to do the exact same thing that we just saw. Where it's going to go, let's go to all the children that I haven't yet seen, which is what this thing is. And what we're going to do is we're going to also say that we can go that path. So in this case, we're saying we can go from 0 to 4 to 2. That's one path. Okay. And then the next thing we're going to do is we're just going to find the next smallest one, which is going to be 9. Right? Obviously, the next smallest one that we haven't seen. Because if you go to the same thing twice, it's kind of useless. So that's just going to be the 9 here. Or the length of 9, but 3. And we're going to do the exact same things, and just to make it simple, we're going to go from 0 to 3 to, well, I guess 1 is a path. We could also go to 7. Right? So we're going to add, oops, we've got to change this to actually a mouse pointer. And we're going to add obviously we're going to skip the 0, we're going to add the 1, and we're going to add the 7. Okay, now from here, the next one is going to be 2. So now we're going to go, okay, we're at 2, we have 0 to 4 to 2 to 5, as well as the same thing, but to 6. Okay, so in this case, it's just going to fill that stuff out, right? And again, just to, if it isn't clear, the way how we visit the nodes is we look at the previous. So this says, hey, to get to 2, you have to go to 4. And then we go to 4. We go, to get to 4, you have to go to 0. Right? So we're just kind of going backwards. Okay. And we're going to add the 2 children I just mentioned. It will visit all the nodes, but obviously it's going to skip over the ones already seen. Now the next morse is going to be, well, it probably will choose the 1 here, but 7's also okay. Yeah, chose the 1. So in this case, it's going to choose, obviously if you use a priority queue, it will choose whatever one was earlier, because that's typically how queues work. But again, it won't really matter. So we choose the 1 here, and we go, okay, we've seen it, now let's look at the past. We've already seen 3, that's okay. But here's interesting. Here is an interesting thing. We have this path to 5 here. Right? We're saying, hey, we can go 1 to 5. So what we're saying is that we're saying we go 0 to 3 to 1 to 5. Now this cost is going to be like 22 or something, right? We already have a path to 5. And that path is 0 to 4 to 2 to 5, which is a cost of 17. So 27, or 22 I should say, because 15 plus 7, is going to be greater than 17. So our path here, the one that we already have, it's great. We don't need to change it. So we can just keep it as it is. So we'll go to the next one. Now the next one's a bit different. And, well, actually it's not different, it's the exact same thing. Yeah. So this path is a distance of 12 plus 6, which is 18. And the other one has a distance of 21, I think. No, it's a distance of 22. It's got the same weight. I don't know why I can't do math. And so 22 is obviously going to be this path here, which is 9 plus 6, which is 15. Add the 7, that's 22, right? But this path here, which is 4 plus 8, which is 12. Add the 6, which is 18. Out of those two paths, obviously the 18 one is better, so it's going to choose the 18, right? There's no need to fix up in this case. And then we go to the next one. And the next one we're going to visit is probably 5, it looks like. No, I can't read. 7. We only choose the smallest cost. I don't know why. I think I read 5 and I was like, that's small. And then we're going to visit 7. 7's not going to do anything. It's just by itself, right? And we'll go back to 3, or who cares. Then we're going to visit 5. And in this case, we actually have a smaller path. No, we don't. Well, maybe we'll see. It does not look like it. Because the cost would be plus 3, which is it's already costing 17 to get to 5, so it's unlikely it's going to change anything. Or it's already known, that's fine. Yeah, so it'll cost 20 to get to 6, so there's no point changing it. So then finally we'll end up with 6, and we'll basically do the exact same math that we did before. We'll say, oh, okay, we've already seen 1, we've already seen 2, we've already seen 5, and there's no need for anything here. And then you can just see it doing here. Right? This is counting all the predecessors. You can see it jumps around as it counts all the predecessors. Right now, I'll just skip forward. And so these will become the shortest paths, which is just what I've got here. So it turns out that this one wasn't necessarily entirely great example because it didn't have any actual overriding. But let's say it did override. So let's say this one was a really small path, like 2. Then what would happen here is it would go 0, let's say 9 plus 6 plus 5, right, is only going to be 20 compared to, let's say this one's like 10, right, compared to 22, or 4 plus 8 plus 10. And since this one is less than it, it's going to decide to do this path instead. So it will change the predecessor. So in this case, 6 would have its predecessor change to 1. And also its cost change to 20 instead of 22. So always choosing the smallest cost. Okay. And finally, we have visualization. Okay. You can't spell apparently. And this is just the same kind of idea as Kruskalls in terms that we want minimum cost, but it's using prims. Right? Now, prims is kind of different than these two algorithms, but it's also not. It uses the same kind of idea that you're using, like you're trying to find a minimal cost of something, you're using some kind of series of arrays. Again, we can use things like predecessors here and so on. Right? And you can call this a set or whatever. Right? Okay. So the first step is basically just to initialize everything. So we're going to say we're going to start from 0 here. So we're going to set the cost to be 0. I could change for this to be a different vertex and maybe give me a better result, but that's okay. And then what we're going to do is we're basically going to go, okay, visit all the nodes near 0 and include them. If the cost of including that node is less than the current cost. Basically, prims is kind of like Dijkstra's. But in Dijkstra's, you include the path up to it, right? So if I want to find between V and W, you include path to V plus the weight of V to Z, right? So including the entire path to V, adding this weight. With prims, we do not add it. It's just the weight. So it's just this. Okay. So what we're going to do next is we're going to go, okay, let's add it here. And you can see it here that we've added it. Basically, you can think of it as if we're building a tree as we go. We're doing 0 and we're doing 3 and we're just adding this. Now we may remove it later on, but I mean we won't in prims because it uses the lowest cost thing, right? But you may change the predecessors a bit for later ones. Wow, people really can't spell. Holy cow. How much charge do I have? Am I going to run out? 7%. Yeah, I'll be fine. Probably. It's fine. We'll code. So here we are. And we're just going to keep going. So if we step forward, we're going to find this path to 3, and then we're going to go from 3. So in the case of 3, what we're going to do is we're going to go, okay, find all the roots around 3 and add them as well. So clearly we're just going to add the path to 7 because we haven't seen that node yet, and obviously 8 is less than infinity, which is the current value. So we're going to also add this one, right? And then we're going to visit the next smallest one. And you can see there's only one choice, really, 8. Like we don't really want to choose infinity. So then we're going to choose 7. And we're going to do the exact same thing. Now we have actual interesting choices. We've got a few nodes. So the first one is the path to 4, which is distance to 6. We haven't seen 4 yet, so we'll include it. The next one is 3. Again, we'll include it. And 4 will include it. Right? So basically what we've said is we said, okay, let's include both of these. Alright. Now, I'll make this cost a bit smaller in a second so we can actually see what happens when it overrides. But we'll pretend this cost is 1 in a second. Okay, then the next thing it'll do is it will visit the next smallest, which is going to be the 3, and visit the 5 and add this path here. As we can see how this goes. And then this will get added, and this will be smallest, so it will also add the 2. Right? So we're going to add the 1 here. And then, oh, I'm stupid. It adds the 1, but that's got a weight of, yeah, ignore that. It adds the 1, but that's got a weight of, I'm skipping ahead because I'm worried about the battery power. It's got a weight of 8, so it means it's going to be visited last because of the priority system. So it means that it's going to visit the 6 next, as you can see, right? Because the 6 is the smallest at a weight of 4. Don't go too fast in these ones, otherwise you will make mistakes. And then the next one it will do is it will find this distance here. Now this distance is going to be a distance of 2, right? and it already has a distance of 6. So previously in Dijkstra's, what it would do is it would go 4 plus 2, right? So it would go, okay, I want to add this path plus this one. This one we do not do that. So in Dijkstra's, either of these are valid. In Prim's, only this is valid. So we're going to choose this one. You're going to see, we're going to add it here, right? And then we're going to visit the last one. That's not going to do anything. And then visit this one and add the 2. And we're done at this point, right? So if I just finish off the tree, now this path here gets eliminated. And we add this path. And that's it. I'll stop now for the sake of my battery not dying on me. Yeah. But that should be it. There's nothing else really. Oops. See assignments. And currency. Okay. And there's nothing else really for this one. There'll be another video, presumably, eventually, for the assignment as well, which I'll go for next. Cheers.